Okay guys, so now it's time for science. Go ahead and open your science books up to page 512. And then open up your vocabulary notebook to a clean page in the science section. The title of today's notes is Science. Oops, we usually don't write that because we're in the science section, so we don't actually need that. But we are on chapter 11, lesson 4. And this is the last lesson of science for this school year. However, it's a little bit longer, so we're going to break this lesson up into 2 days. We're going to do the first half today, and then we'll do the second half on Friday. And then remember, your test is next Wednesday, April 22nd, so don't forget about that. Okay, so you should be open to a clean page in your notebook with the title of the notes as well as today's date, and your book should be open to page 512. This chapter is on simple machines. Let's look at the look and wonder. Rowing a boat can be a lot of work. It takes some force to get the boat moving. How can you reduce the amount of force that you need to do work? I want you to think about that for a second. Think if you can think of an answer for that. Okay, let's go ahead and turn the page. And on page 514, let's go ahead and read the main idea. Simple machines make it easier to do a task. Levers, wheels, and axles, pulleys, inclined planes, wedges, and screws are the 6 kinds of simple machines. What are simple machines? Name some machines that people use. You might think of a computer, a lawnmower, or a car. Those machines have lots of parts. I mean, just think about how many parts all of those things, a computer, a lawnmower, a car has. I mean, I can name even the engine alone, which is just part of a car or a lawnmower, has tons of little tiny pieces in there working together. To a scientist, a machine is anything that helps us to do work. Let's add that in to our vocabulary. So number 1 is the word machine. And scientists don't necessarily think of a machine the same way we do. Like when we think of a machine, we think of one of those things with lots of parts, like a computer or a lawnmower or a car or a weed whacker or a forklift or anything like that. They have tons of parts. But to a scientist, a machine can be anything that helps us to do work. Anything that helps us do work. Meaning the scientific version of work. I mean the scientific meaning of work, not like going to work at an office or at a school or something like that. A pulley is a simple machine that helps you move objects. A simple machine has only a few parts. So number 2, the word is simple machine. And a simple machine is a machine that has only a few parts. So those things we mentioned earlier, the car, the lawnmower, the computer, the forklift, the weed whacker, whatever, those are not simple machines because they have tons of parts. A pulley is a simple machine. Other simple machines are the lever, the wheel and axle, the inclined plane, the screw, and the wedge. And so first we're going to talk about levers. Have you ever used a screwdriver to open a can of paint? So remember, you take the can of paint, maybe you've seen your parents or you've seen it on TV or something, and you put that screwdriver under the lip of that paint can, and then you push down on the screwdriver to get the paint can to pop up. If so, you have used a lever. A lever has 2 parts. It has a bar or plank and a fixed point called a fulcrum. So So, number 3 is the word lever, and it is a simple machine with 2 parts. We might add to that definition. So it has a bar or a plank and a fixed point called a fulcrum. The fulcrum supports the bar and allows it to turn or pivot. The diagram below shows the 3 kinds of levers. So let's look at this diagram. We can see, if we look, let's look at the one all the way to the left where he's got the, they look like pliers. We can see the bar or plank that goes across, and then the fulcrum. So we've got the fulcrum, which is that triangle, and then we've got that bar or plank. Whoops, they don't quite meet. That bar or plank that goes across. This is the lever. Now over here we have the load, which is whatever object we're trying to lift. Notice that that this fulcrum, this lever looks kind of like a seesaw. So imagine it like a seesaw where you are here. You're just sitting there. If you get on the seesaw by yourself, well, you're going to be way down here. Nothing's going to happen. But then when somebody else gets on here, it pushes this side down and you go up. So what this is demonstrating, where you are on one side and then somebody pushes down on this side, making you go up, is an example of a first-class lever where the fulcrum is, is between the load, you, and the force, the effort force, which is what's causing you to lift. We can see this working in this picture of the pliers. We have they're using pliers as a nutcracker. So find the nut and find the hand. Right in the middle, you see that little screw. That is the fulcrum. So if we have some pliers, I'm going to try to draw this picture. It's not very good. But, oh well. Here's the fulcrum. Here's the load, that nut. And then your hand is going to push on this side. So there's that effort force. When you push here, these are connected and these are connected. So as you put force here, it's going to squeeze these pieces together up at the top so that it cracks that nut. Okay, now if we look at the second class lever, which has its fulcrum at the end and the load in the middle, this is what that looks like as if we imagined it as a seesaw. So here's the fulcrum, here's the plank. You, the load, are in the middle. What would happen is force, the effort force is on this end. If it is pushing up, it is lifting you. Now, if we look at we have an actual nutcracker down there. And it looks like this. It's got its fulcrum at the top. And then these pieces come down like this. I'm trying to draw it so that it's attached. Here's the nut, and then the force, your hand, goes down here. So what happens is, as you squeeze, that fulcrum stays there, but it makes these pieces come together so that they again crack that nut. Okay, and now if we look at the third class lever, which has its fulcrum at the end, the effort force has to be in the middle. So, if we imagine it as that seesaw, here's the fulcrum, here's you. You have to push up in the middle. Somebody has to push up in the middle in order to lift you. If we look at this, these look like maybe like tongs or like tongs of some sort. It looks like this. The fulcrum is down here. Here's the nut. Oops. And you have to push in the middle. when you push in the middle, that fulcrum allows these pieces to go together and then crack that nut. Now, let's look at load and effort force. I'm going to erase this really quick so that we can fit the next words. So, load and effort force. To describe how levers work, scientists use two other terms. The object being moved by a lever is called the load. So, in our drawings that we just did, the U on the seesaw, that was the load, or the nut in the picture of the different ways to crack a nut was the load. So our fourth vocabulary word is load. And load is the object being moved by a lever. The force used to do work is called the effort force. So number 5 is effort force, which is the force used to do work. So whether that's the force needed to lift you on the seesaw or the force needed to crack the nut, that was all effort force. A lever doesn't make you stronger. So just because you have a lever and now you can lift something heavy, that doesn't necessarily mean that you all of a sudden got really strong. It changes how much effort, how much effort force you use to move a load. So that means the lever makes it so that you don't have to use as much effort to lift it. So you're not necessarily stronger, you just don't have to use as much effort. What happens if you apply a small force over a long distance? So that's not too much force, you're not doing too much over a really long distance. The lever applies a strong force over a short distance. This happens when you use a lever to pry open a can of paint. So, you're not using that much force to push that screwdriver down to open that can of paint. But the lever itself, that screwdriver, uses a lot of force in just that spot where the paint is being opened. You can also use a lever to apply a force over a small distance. The lever then applies a weaker force over a long distance. This happens when you hit a tennis ball with a racket. Okay, so let's look at the quick check. Remember, I ask these questions, you pause the video and answer them in your notes, and then you play it and check your answer. Compare and contrast. How are the three kinds of levers similar? How are they different? So that means how are the first class lever, the second class lever, and the third class lever alike, and how are they different? Well, they're similar because they each have a load, an effort force, and a fulcrum. But they're different because the three parts are arranged in different ways for each one. In the first class lever, the fulcrum is in the middle of the effort force and the load. In the second class lever, the load is in the middle of the fulcrum and the effort force. And in the third class lever, the effort force is in the middle of the load and the fulcrum. Now the critical thinking question. What kind of lever is a tennis racket? And explain. So is it a first class lever, a second class lever, or a third class lever? So figure out the fulcrum is what actually allows it to move. And then, Okay, a tennis racket is a third class lever. The load is the ball. The effort force is between the ball and the player's wrist. And the fulcrum is the player's wrist. So the fulcrum is your wrist because that's what's actually allowing you to move the tennis racket. The fulcrum is what allows the lever to move. The load is at the end, and then the effort force is in the middle, as that between that tennis ball and your wrist. Okay, go ahead and turn the page, and we're going to learn about a few more types of simple machines. So let's read on page 516. What are two other simple machines? Wheels and axles are everywhere. Pulleys are less common. Wheels and axles. When you turn a doorknob, you are using a wheel and axle. A wheel and axle has two parts. You probably guessed that one part is a wheel, the other part, the axle, is a bar that passes through the wheel center. The bar is fixed to the wheel. Fixed to the wheel means they are attached. So let's add wheel and axle to our vocabulary words. And it is a simple machine with two parts, the wheel and the axle. And what's that saying is there's a wheel, and right in the middle there's an axle, and they are attached. Wheels and axles help you move things. You only need to use a small force on the wheel. The axle turns it into a larger force. The larger force moves the load. So if you're imagining this as a doorknob, the axle goes right through the middle. You don't have to turn the doorknob that hard because the axle is what's going to actually help to open that door. Have you ever been on a Ferris wheel? The cars are attached to a giant wheel. The wheel hangs on an axle. When a force is applied to the axle, it turns the wheel. The axle moves only a small distance, but the wheel moves a lot more. The work of this machine gives us pleasure. So think of this as a Ferris wheel. The wheel itself is not what's being moved. The motor that runs that Ferris wheel moves this axle. So it just turns, that axle just turns in place, and then the wheel turns with it. So the actual Ferris wheel moves a lot, while that axle it's just turning in its spot. Okay, next we have fixed pulleys. As you have seen, a pulley makes it easier to lift a load. There are different kinds of pulleys. So first, we have a fixed pulley. In a fixed pulley, the wheel is attached to something. It cannot change position. On one end of the rope, one end of the rope is passed through the wheel. The other end is tied to a load. Pulling the rope lifts the load. So if we look at this diagram on the top of page 517, that first picture is of a fixed pulley. So that pulley is in place. That wheel does not move. It is right in place. There's a rope thrown over it like this. Oops, my drawings don't really match up very well, but you know what I mean. And as somebody pulls on this rope, whatever's attached to this side goes up. As you pull over here, that effort force, pulls over here, that load is lifted. Other types of pulleys. A fixed pulley simply changes the direction of a force. You pull down, the load moves up. So that's what happens with this fixed pulley. You pull down, so you're pulling down, but your effort of pulling down is making this object go up. So it just changes the direction of the force. Your force is moving down, but your load is moving up. This kind of pulley cannot change the amount of effort force needed to move a load. So no matter what, you have to use the same effort, no matter what the load is. The rope pulls on the object with the same force as you pull on the rope. So however hard you're pulling on the rope, that's how fast this object is going to go. Pulling on that rope does not change, this pulley does not change how fast this moves. A movable pulley is not attached to a fixed object. It moves in the same direction as the load. A movable pulley reduces the effort force needed to move a load. So let's look at that second picture. That's the movable pulley. Instead of the rope going over the pulley and changing the direction of the force, the pulley is not attached to anything up here. The rope is attached and then the rope goes under. The load is here, and as you pull up, as the effort goes up, that's how that load is moved. So you don't actually have to pull as hard because that pulley can move along the rope. What happens if you hook a fixed pulley to a movable pulley? Look at the diagram. The third drawing shows the answer. So let's look at that third drawing. We have a fixed pulley, which is attached to this bar up here. And then we have a movable pulley that is just on the rope. So let's look at what happens. And then that load is on the movable pulley, not the rope. The load is on the movable pulley. The rope runs through both. You need to pull the rope far away to lift the weight a small distance. So, because they're so close, you have to pull from way over here. Like here's our pulley, and I have to go way over here to pull it because they are so close to each other. So let's look at each of these types of pulleys. You might see this again later, so pay close attention. It says compare and contrast the effort force of the three types of pulleys. So let's look at them and see how much effort force you need for each of these three types of pulleys. Well, with a fixed pulley, the effort force is the same as the weight of the load. You have to pull just as much as that load is pulling in order to get it to lift. But the force goes in the opposite direction. You're pulling down, the load moves up. A movable pulley decreases, so you don't need as much effort force to move the load, and the force goes in the same direction. So that means this pulley is going to move, or this load, the pulley attached to the load, is going to move in the same direction that you are pulling from. But it's not going to require as much force because it's going to move itself. It's going to roll along that rope. With a compound, which is a fixed and a movable, that means you put two simple machines together to create a compound machine. So with a compound pulley, the effort force is less than that of a movable pulley, and the effort force is in the opposite direction of the moving load. So that means they're all kind of combined to create opposite of what either the fixed pulley or the movable pulley does. Okay, let's look at the quick check, and then we are done with this lesson for today. So remember, I'm going to ask the question, you pause the video, answer the question in your notes, and then play the video to check. So compare and contrast. How does a wheel and axle differ from a pulley? So think of the wheel and axle, and then think of the pulley. How are they different? So a wheel and an axle are attached to each other. That means they do not come apart. Like that Ferris wheel, that axle that actually turns the Ferris wheel, they're attached. But a pulley spins freely on its axle. That means the axle moving doesn't make the wheel spin a certain way. The way they trade effort force or change direction of force is different because the pulley is not attached to that axle in the same way that a wheel and axle are. Okay, now the critical thinking question. A doorknob is a wheel and axle. Which part of it is the wheel and which part is the axle? Think about that. Think about what you know about a doorknob. Think about what you've learned about wheels and axles. Which part is the wheel? Which part is the axle? So for this question, what you needed to do is you needed to think if you've ever seen a doorknob that's not attached to a door. It looks like, I'm going to do a terrible picture, but it looks like this, and then there's this piece that comes out. So the knob itself is the wheel, and then this piece, even though we can't see it, goes through this doorknob. So that is the axle. Okay, so that's all we're doing for today. We'll do the rest of the lesson on Friday. So go ahead, get out your packet for Wednesday, April 15th. Open it up past the reading, and then you have some independent practice using the diagram of the pulleys. So use the diagram, use what you read in the textbook in order to answer these questions. There is no back, so as soon as you're done with that, you can go ahead and do the homework, or you can wait until later today. The homework today is not an outline. It is vocabulary. It is front and back. It is vocabulary from this lesson. You may have to skim some of the vocabulary words or some of those, either the highlighted or the words in italics in the parts that we have not read yet. But you do not have to fully read the rest of the lesson in order to do this homework. You just may have to skim those vocabulary words or some of those italics words that we have not come across yet. Remember, italics is that slanted writing. Okay, if you have any questions about today's lesson, then reach out to me today between 1 and 5. You can Skype me or FaceTime me, however you need to get in touch with me if you need to.